Okay, welcome you all to the second session for thin film solar cells for Pvcon 2020. I'm hoping everyone enjoying the talks up to so far. It's been going quite well. And today, our first speaker is going to be Gizem Aydın from Şişecam, Turkey. Şişecam is one of the leading institutes in glass technologies in Turkey, and there's a lot of interesting research is being done in addition to a sizable production. And Gizem's talk her talk is entitled as Temperable Single Layer Anti-Reflection Coatings for Solar Panel Applications based on a dual alkoxysilane precursor chemistry. And with that, the floor will be Gizem's, and I think it's a pre-recorded session, so we'll move from there.
Hello everyone. I have pre-recorded presentation, and I also introduced myself in this presentation. So I'm ready for watch. Hello everybody, my name is Gizem Aydın. I'm a material science engineer and a researcher at Şişecam R&D Center. Our study is related with thin film coatings. Dr. Budakoğlu, Dr. Okan, Professor Kazman, and me studied on an anti-reflective coating that includes dual alkoxylanes and has temperable properties. First, I will talk about our scope and goals, and then I will give a short theoretical information. After that, I will explain experimental studies and results. Finally, I will complete my presentation with the conclusion part. The main scope of this study is developing a single-sided and one-layer anti-reflective coating without any nanoparticle addition. We defined some objectives before starting this project. You can see on the chart this coating should have been easy to produce and apply on the surface of glass. Also, it should have minimum 2% increase in transmission. Also, due to coated float glass requirements, the coating should have temperable property and high durability and mechanical properties. Let's continue with theoretical information. You can see all layers of the PV panel system. The cover glass is that we interest because the anti-reflective film will be applied on this layer. I also want to talk about the production of Şişecam cover glass. As a substrate, we used pattern glass, and you can see pictures of glass on the production band. The hot glass is shaped while passing between two rows, one with a pattern and the other without pattern. We applied AR film on the surface without pattern. I want to give some brief information about optical concepts and some formulas. Basically, single-side coating system consists of three mediums. These are the air, coating film, and the glass substrate. From the related equations, we know that the ideal refractive index value of film should be 1.23. And we use the AMS spectrum to calculate ideal coating thickness, which is about 100 nanometer. Because the angles and intensities of rays coming from sun are different at different regions of Earth. For equatorial regions, we use AM 1.5 standard calculations to understand wavelength distribution. Among the existing materials, there is no coating material with a refractive index of 1.23, so we have to obtain a porous film to decrease refractive index. Pore structures can be open or closed types. You can see on table that there are advantages and some disadvantages compared to each other. We try to eliminate low strength of open structure by chemical modification. You can see in schematic view of molecules on right corner side of page. There are two different types of silane molecules in figure. Red ones have one organic group. During the process, these groups will decompose and small gaps will remain behind. This is the system that we studied on. Let's continue with experimental studies. First, glass substrates and solutions were prepared. Since we used deep coating method, one side of glasses was masked. After coating, coated glasses were cured at 100 degrees Celsius and tempered at 700 degrees Celsius for 3 minutes. In order to obtain optimum conditions, we studied all parameters such as withdrawal rate, temperature, and time, etc. Also, we did many tests, analyses, and used characterization techniques that you can see at the end of the flow chart to investigate details. Here is the solution preparation and coating steps. We used as a solvent ethanol, propanol, and PMA mixture, and as a precursor, we used dual alkoxylanes, which are tetraethyl orthosilicate and methyl triethylsilicate that you can see in figures. Finally, we added acetic acid as an organic acid and nitric acid as an inorganic acid together as catalysts. We determined the exact ratios of all ingredients by experimenting, except slanes. We have determined the slane groups as variables, and you can see 5 different ratios coded as G in table. We use deep coating method, as I said before, and here steps of this method. The substrate is immersed into the solution. The substrate which has been dipped into the solution starts to be pulled up. The withdrawal is carried out at a constant rate. The film is deposited on the substrate while it's pulled up. The solvent is evaporated from the deposited liquid film, resulting on the coating. The most important parameter is withdrawal speed that you can see in equation. The withdrawal speed determines the thickness of the deposited film. A higher speed produces a thicker film. As I mentioned before, our withdrawal rate was 150 millimeter per minute. With this method, we coated our samples with the periods you see in table and examined the effects of the waiting time of solution. Let's continue with results. There are two FTR graphs in here. The left one that includes all versions shows us the peaks belonged organic groups are increasing with increasing Mtes ratio, and the other one, which belongs to G-free version of solutions after several temperatures, shows that organic groups moved away from solutions with increasing temperature. But even after 700 degrees, it is thought that there are still some organic groups left that seems on the green line. Also, there are nanoparticle size distributions for all versions. We can say that the average nanoparticle size increases with increasing Mtes ratio. You can see droplet images in here and contact angle values of all coatings. Columns represent solution versions with different Mtes, TEOS ratios, and rows represent with coating times. We can say that the hydrophobicity of surface is increasing with increasing Mtes content. It can be thought that this is due to organic group increase. On the other hand, the stability of G5 solution is lower than the others. Here are optical microscope images. You can see regions that are difficult to adhesion in version G5. It's because of non-bounding branches in Mtes. Thus, we can say that the adhesion decreases with increasing Mtes ratio. Here in the first graph, there are a lot of data in the visible transmission of coatings belongs to all versions in different coating periods. And also there is another graph in below. It shows transmission measurements of coatings weighted in atmospheric conditions for 1 week. We can say that G-free version has the best values in transmission, and there is no significant difference even 1 week later for all versions. In this part, there are another transmission and reflection measurements in different wavelengths. And again, G-free sample has the best values in both transmission and reflection. G-free coating provided 1.9% in TAM 1.5 transmission scale, also provided 2.26% in light and 1.73% in solar reflection. Here are the cross-section SEM images of G1, G3, and G5 samples and TEM images of G3 samples. We have obtained the maximum transmission value with the G3 sample, and its coating thickness is about 100 nanometer. It's also shown in TM images that G3 samples has no porosity in nanometer scale. You see a device here. It can be measured the thickness and refractive index of coatings by device. Actually, that device uses some equations to calculate this, some approximate limits and entered to its program. Then it generates data in reflection mode with the help of a probe and makes calculations by matching with the entered values. It seems that the values closest to 100 nanometer belong to the G3 sample, and minimum refractive index value obtained is 1.40. Here is the results of neutral salt spray test that is one of the most important corrosion tests for coated glasses. When we compared all samples, it seems that the transmission loss, in other words, corrosion resistance, decreases with increasing Mtes ratio. We also did a linear wear test. The values on the table are a little bit different because the samples mask for this test. The difference between measurements before and after test are used to compare. It seems that there is no remarkable difference for all versions. Here's another mechanical test that is called Newton's scratch hardness test. You can see the scratches on surface of coatings after test in figures. The columns represent versions of solutions and rows represent different laws. It doesn't seem any scratches in G5 sample after 3 Newton loads. And then we look at even the alkaline substrates after 20 Newton load, we can see scratches of glass as black line. This type of scratch only appears in G1 sample, not for the others. So we can say that the scratch resistance increases with increasing Mtes ratio. We can summarize all results as follows. In this study, we obtained hybrid structures by using dual Alcox lanes and different type of acids, and also we reduced the corrosive effects of solutions by using organic acids. It's important for mass production, such as roll coating. Comparable anti-reflective coating were obtained, and we saw that the Mtes component provides coating thickness, tolerance, and elasticity, but its excessive increase affects coating adhesion and solution stability negatively. It's proved that the optimum Mtes TOS mole ratio was 1.2 among all versions. It was achieved successful results from corrosion and mechanical tests for all versions. The fact that no pore was detected in the TEM image of the G3 sample suggests that the pore structures were at the molecular level. Last but not least, transmission increase up to 2.8% has been achieved through anti-reflective coating without using any pore agents. Thank you for your attention.
Thank you very much for the nice presentation. There's one question from the audience that I want to direct to you. It says, how does the MTES ratio affect coating elasticity? Is it directly proportional?
The MTS compounds include methyl groups, and most of these organic compounds decompose from film structure at high temperatures. And by this way, small gaps remain behind in the structure. These gaps provide possibility to movements and flexibility of molecules during the heat treatments, and other organic branches connected to each other and glass substrate. On the other hand, if Mtes ratio increased too much, the bonding branching numbers decreased, so the adhesion of coating is affected badly.
Okay, I think that was quite clear. I have a small question. So it seems like, you know, these coatings that you have been developing has you know, a positive effect on many parameters and just performed quite well in many of your tests. But how about the cost effectiveness of this coating process? I mean, does that include does that contribute too much cost to the overall preparation of the glass for solar cells?
Mm-hmm. With which technique compare to nanoparticle additive
Yes.
solutions? 5 over, actually, about.
5% increase in cost, you mean?
No, sorry. Actually, I need to check the exact ratio. Hmm, 4 times cheaper than with nanoparticle additive.
Oh, so it's also cheaper.
Yes.
Okay, that sounds great. Okay. Are there any other questions from the audience? I'm assuming if there's anything that will be written. I guess not. Okay. I guess that's it. Thank you very much for the nice contribution. And,
thank you so much.
Sure. We're going to move on to the next speaker. Next speaker is Yasin Kahas. Sorry about the pronunciation. Yasin Kahasa. Is that correct? Are you here? I'm not seeing your name, but you probably are here. Yeah, Yasin Kahasa from Tofayl University, Morocco. And the title of the talk is A New Efficient Synthesis of Zinc Sulfide Thin Film Using Mist Chemical Vapor Deposition Technique. And assuming this is also a pre-recorded talk, so yeah, I guess we can just go ahead and start a talk, but I'm not sure if our speaker is online here right now for questions. We'll see about that. Well, anyways, so we can just go ahead and start with the presentation.
First of all, I would like to thank all the committees for their excellent organization. My talk is about a new efficient synthesis of ZNS thin film using Mtes CVD technique. The main objective of this presentation is to share with you our results on the development of the N-type ZNS material synthesized by Mtes CVD technique for photovoltaic applications. In this presentation, I start by an introduction in which I present the objective of the work. Then I will explain the experiment parts for the elaboration of the ZNS thin film. After, we will see together the results of the analysis, and I will finish by a conclusion. In a photovoltaic device, the solar cell is composed by 4 main layers in addition to the substrate, which is generally made of glass. There is the back contact, which is anomic contact. In most cases, it's molybdenum. The second layer is the absorbent layer with P-type conduction. The third is the buffer layer. And the last layer is the transparent oxide conductive layer in ITO or ZNO doped aluminum. In this presentation, we focus on the buffer layer, which is layer located between the absorbent layer and the transparent conductive oxide layer. This layer influences considerably the performance of the thin film solar cell. Generally, the most solar cells use CDS as buffer layers, but to avoid toxic cadmium, we replace the CDS layer with a ZNS layer. In this work, we have interested in the elaboration of the films of zinc sulfide and studied the effect of the solvent and temperature on the optical, morphological, and structural properties of our layer which have been prepared by the Mtes technique. The spray-assisted CVD technique is a technique developed by Japanese researchers. The technique operates at atmospheric pressure and at room temperature. The figure in front of you shows USCVD system. In USCVD system, there are three principal parts. The first is the gas unit. It's composed of a gas cylinder and a flow unit with two flow meters, one for gas carrier and the other for dilution gas. The second part of the system is the mist unit. It consists of a hollow solution cylinder covered by a thin plastic film in solution side and a small tank of water with two ultrasonic generators. The third part is the reaction unit. It's composed of heater and reactor chamber. This technique has many advantages as the simplicity, low cost, does not require vacuum at any stage, security and easy operation, the simple system configuration with easy maintenance, good addition between the film and the substrate, the quality of the film. First of all, the substrate is cleaned according to these steps. Watch 14 minutes in acetone bath. Watch 14 minutes in methanol bath. Rinse 14 minutes in distilled water bath. Dry the substrate using an oven at 110 degrees Celsius. Then, ZNS solution were prepared using zinc chloride as the zinc source and urea as the sulfur source. The required quantity of precursor was dissolved using distilled water or methanol or mixed distilled water and methanol in a glass beaker. After, our substrates are placed on the heating plates in the reactor at the desired temperature. Then we initiate the USCVD parameter and we start the operation which is explained in the previous slide. The deposition time was 20 minutes. The used parameters are resumed in the table in front of you. In this study, we present the results for different solvents with a substrate temperature set at 415 degrees Celsius. The figure shows the X-ray diffraction profile of ZNS thin film grown in different solvents. ZNS is known to have zinc blend and weird Z structures. The peaks of ZNS blend were observed for samples grown at different solvents, and weird Z ZNS peak was observed in samples grown at 100% methanol solvents. Note also weird Z ZNO peaks were clearly observed for two solvents, 100% distilled water and 15% distilled water, 15% methanol. This result indicates that all ZNS samples have a zinc blend structure and the sample grown in 100% methanol also contain weird Z structure. The transmission spectra for the prepared layers has been shown in the figure. The general shape of the spectra is similar. We can distinguish two transmission domains depending on the wavelength. A domain characterized by high absorption and low transmission of light radiation, which corresponds to the wavelength less than 400 nanometers. A high transparency domain located between 400 and 900 nanometers, in which the transmission takes the values between 17 and 18%. From the transmission spectra, we have calculated the optical gap using Tox formula, and we can observe that the gap for all films varies in the range of 3.43 to 3.62 electrovolts. These values are close to the values reported in the literature. These figures represent the morphology of ZNS layers deposited by USCVD with different percentages of the solvents. It is observed that all the films exhibit better adhesion to the substrate, very dense and very compact particles covering the entire surface of the substrate. In this part, we have investigated the temperature effect which a solvent of 75% methanol, 25% distilled water. The figure shows the X-ray diffraction profile of ZNS thin film grown at different temperature from 400 to 500 degrees Celsius. Zinc blend ZNS peaks were observed for all samples grown at 415 to 500 degrees Celsius, and peaks of wet ZNO were observed in the sample grown at 400 degrees Celsius. These results indicate that all ZNS samples have a ZN blend structure and that the sample grown at 400 degrees Celsius also contain wet ZNO structure. From the transmission spectra, we notice that the transparency of the film increases with the increase in the temperature of the substrate, and that the maximum of the transmittance is located in the visible range. We have calculated the optical gap from the transmission spectra using Tox formula, and we observe that the gap of all films varies in the range of 3.57 to 3.65 electrovolts. The figure in front of you represents the morphology of the layers of ZNS deposited by USCVD with different deposition temperatures. We can see that all the films exhibit better adhesion to the substrate, very dense and very compact particles covering the entire surface of the substrate. The same images show the presence of a mixture of grains of hexagonal and cubic shape for the temperature 400 degrees Celsius, with a predominance of cubic grains toward the high temperature. These results confirm the analysis obtained by X-ray diffraction measurements. Therefore, from the present study we can conclude that the spray-assisted CVD method allows us to produce zinc sulfide layers in the air with good quality. For elaborated ZNS thin film, the mixture of methanol and distilled water, 75% methanol, 25% distilled water, is the best choice. The optimum deposit temperature is 415 degrees Celsius. Thank you for your
Okay, so I'm wondering if we have Yassine here with us for questions. Our speaker here. I guess not. Okay, so I guess that was a connection problem. So we're not going to be able to direct any questions. But if you have any questions, I'm pretty sure you can just find the email and just send me an email. I guess we're just going to continue with the next speaker. The next speaker is from Nida Ömer Halis Demir University in Turkey, Mehmet Ali Olar, and his talk is entitled as Effect of Stacking Order and Reaction Temperature on Properties of Ccts thin films. And Mehmet Hoca is here with us. Hello.
Hey, everyone. Thank you.
Yeah, so the floor is yours. I think your talk is also pre-recorded or not?
Yeah. I have sent it before.
Okay.
Thank
great.
you.
Okay, so we can just go ahead with the talk and then discuss questions later.
Okay. Thank you.
Hello everybody, my name is Mehmet Ali Ulgar from Needham Halistimir University. First of all, I hope all of you are well due to this pandemic situation. Today I will talk about CCTS thin films. Due to I have a limited time, so I will go a little bit fast. Now I am going to my presentation. Yes, this is my presentation. My talk is effect of stacking order and reaction temperature on properties of CCTS thin films. My colleagues are Ali Orgunsarp, Ayşe Seyhan, and Recep Zane from the same university. In this talk, I will briefly explain the effect of the stacking order and the reaction temperature on the properties of CCTS thin films. This is my outline. In my outline, first of all, I will give a brief introduction about solar cells and the CCTS. And then I will talk about the idea and novelty of this study. Then I will talk about my experimental details, what kind of experimental stuff we performed in this study. Then I will discuss my results. Finally, I will conclude my presentation. It's well known that the solar cells can be classified under three main titles, or maybe you can increase these titles, but generally we classify the solar cell under silicon, semiconductor or thin films, and emerging and novel materials. The silicon solar cells dominate most of the PV technology. It's well known, and there are silicon and amorphous silicon. Under the crystalline silicon, you can see like a single crystalline or multicrystalline. Under the amorphous, you can see the hydrogenated amorphous silicon. In the thin films, you can see the chalcogenides or compounds 3,5 semiconductors. These are cadmium telluride, CIGS, and copper zinc tin sulfide, CCTS, or gallium indium phosphide, gallium arsenide, or others. In the emerging or novel materials, there you can see like desynthesized solar cell, colloidal, quantum dots, perovskites, and organics. It can be seen that there are so many different kinds of solar cells, but each kind of solar cell has some advantages and disadvantages here. In our presentation, I will talk about the copper zinc tin sulfide, since the cadmium telluride and the CIGS-based solar cells have already reached over 20% conversion efficiency, but due to like a scarcity of indium and gallium and toxicity of cadmium may restrict further development of such kind of solar cells. So the copper zinc tin sulfide, or CCT, is emerging as a new and alternative materials to these compounds. What are the properties of the CCTS? First of all, we use the CCTS as an absorber layer in the CCTS-based solar cell. This is just a layer. So it is a p-type conductivity, and it has a p-type conductivity, and we use to absorb the most of the photons. So it has a suitable band gap. As you can see in this figure, the 1.4 is around here, and the theoretical limit is at about 30%. But for this kind of solar cells, the reported conversion efficiency around 12.6. So there are so many things to do to increase the reported current conversion efficiency. It has a high absorption coefficient. It means that you can absorb the most of the light in a very thin layer. It has a low cost. It has a low cost and earth abundant materials. So as you can see, there's a copper here, zinc here, a tin here. It has a crustal abundance, and the price is low in compared with other like indium and gallium. So due to the low cost and earth abundant materials, it is preferable in the thin film photovoltaic applications. It's environmentally friendly raw materials it has, so it can be used very widely in the thin film solar cell due to these properties, and it has also a simple and fast fabrication process. What was the idea and note of this study? In the literature, you can see so many different stacking order in the literature. In generally, the metallic layers can be deposited sequential as this. You can see just a few stacking orders selected from the literature, but here each stacking order has a big impact on the properties of CCTS thin films. So there should be choose the most promising one in order to getting high conversion efficiency. So in this study, we propose two new stacks. First proposed by our research group. The first one is a copper tin zinc copper. First of all, we deposit copper and tin, and then we turn the sputtering chamber without breaking the vacuum, and then we obtain copper tin alloy in order to prevent the tin loss from the samples, because the tin has a high vapor pressure. So in order to prevent the tin loss, we alloy them with a copper and then zinc deposit on it. Finally, the remaining part of the copper deposit on zinc. We mentioned this stack is an E-type because we used here elemental zinc, and in the next one we use the binary layer of zinc. So we used a B-type. We donated these samples like a B-type because we used a binary target here. So in this study, we investigate effect of the reaction temperature and stacking order of films, stacking order of this film. So we use various sulfurization temperatures and we compare both stacking order to find the best one. What was the experimental details? We sputtered the metallic films layer by layer with a PVD system. It is in our laboratory to form this two stacking order, copper tin zinc copper and copper tin zinc as copper. We anneal them in the RTP system at 500, 525, 550, 575 for 1 minute, because the RTP gives such a nice facility with a heating rate 3 Celsius per second in a argon and hydrogen atmosphere. And then finally, we analyze these samples with a profilometer to measure the thickness of the films, EDX, the chemical to measure the chemical composition of the films, SEM, scanning electron microscopy to investigate morphology of the films, XRD to investigate crystalline structure, and Raman also to investigate structural properties of the films. And finally, photoluminescence room temperature photoluminescence spectroscopy to investigate optical properties of these films. As I said before, we use two stacking order E-type and B-type samples, and we use 4 different temperatures for each sample. So we donated the samples, we numerated the samples like as is this 75, 76, 77, 78 according to their sulfurization temperature for E-type, and CCTS 79, 80, 81, 82 for B-type samples according to their sulfurization temperatures. In our EDX measurement, we target to obtain copper poor and zinc rich samples, because in the CCTS thin films, the copper poor and zinc rich composition is a desired properties, since copper vacancies and copper zinc andesite defects strengthen the P-type conductivity of this compound. So this is our target. As you can see, this is the chemical composition of the prepared CCTS samples for E and B-type samples. At the left side, there are E-type samples, and the right side also the B-type samples. As you can see, for the E-type samples, all of the samples have a copper poor and the zinc-rich composition. But as you can see, at 500 Celsius, the samples obtained, the copper ratio is less than the others, and the sulfur ratio is low with comparing to other samples. So it can be concluded that here the sulfurization temperature for 1 minute at this temperature is maybe insufficient to obtain fully completed CCTS samples. So for E-type films, maybe 500 Celsius is not sufficient. And also for B-type samples, you can see all of the samples have a copper poor and zinc rich composition except of this sample. And in these samples, you can see the zinc ratio is the stoichiometric ratio. So maybe it can be excluded due to this composition. The X-ray diffraction, we take it to examine the crystal structure of the films. As you can see, for the E-type and B-type samples, regardless of the sulfurization temperature or stacking orders, all of the samples dominated by diffraction planes of the Kessler CCTS phase. As you can see, here's the 112 plane, 220 plane, and 212 plane. For both samples are dominated all the patterns. Apart from the Kessler CCTS phase, as you can see, at low reaction temperatures, you can see some copper-based secondary phases occurred, and also tin-based secondary phases like copper sulfide, tin D sulfide, and copper 2 sulfide. But here I want to draw your attention, as you increase the temperature about the 550, you can see some tin sulfide also appear again. This is important result since, according to Schur and his colleagues, you can see here as the increasing temperature, these reactions are reversible. So if you increase temperature about a certain temperature, some decomposition reaction can be occur. So in these samples, maybe some decomposition reactions occur since tin sulfide phase forms here. In the P-type samples also, you can see at low reaction temperatures, some copper sulfide and tin sulfide phases occur below the 550. It means that for this type of samples, the sulfurization temperature about the 525 seems much better. To investigate the crystalline quality of the films, the Pi-Scherrer formula is used here. As you can see, according to the Pi-Scherrer formula, the crystalline quality is inversely proportional with the Filipet half maximum values here. As the temperature increase, you can see the Filipet half maximum decrease. It means that the crystalline quality is also enhanced. For the B-type samples also, you can see as the Filipet half maximums also increase, the Filipet half maximum decrease until the 550, then the Filipet half maximum is increased. It means that for B-type samples, the 550 Celsius seems much better. For E-type samples also, we can make a conclusion, because after the 550, some decomposition reactions are also observed. So for E-type samples also seems the 550 is the proper one in terms of the pure crystalline quality. But of course, the XRT is not enough for for distinguishing the CCTS phase, because CCTS, zinc sulfide, and CTS thin films sharing the similar XRT patterns. So we need a complementary technique. This is the Raman spectroscopy. As you can see, the Raman spectroscopy also gives us the phases and distinguish these phases from each other. As you can see, regardless of the sulfurization temperature and the stacking order, all the samples again dominated by peaks of CCTS. As you can see, around 338, it stems from the vibration of sulfur anions in this compound. Apart from this gas steroid phase, you can see at low reaction temperature some copper sulfide phase occurs, and at high reaction temperature some CTS phase occurs. According again this formula, you can see the copper tin sulfide phase occur in these samples. It means that for E-type samples, maybe the sulfurization temperature is not enough. So maybe we should extend the sulfurization temperature to obtain fully CCTS structure. In the B-type CCS samples, you can see the copper sulfide is not observed, but CTS phase occurs in all samples. Apart from these samples at 575, you can see additionally copper sulfide phase. This is according to Scrag et al.'s formation of like a copper sulfide may sign the decomposition reaction in CCTS compounds. So the 550 maybe is much better, or maybe you should limit the temperature at this temperature. This is the SEM picture of these samples. As you can see, as you increase the temperature, you can see the grains becomes larger and larger. This is the same situation also for the B-type CCTS samples. Here, as you can see, this sample is the best one for the solar cell application for B-type samples, and here also we can see this samples seems much better in terms of the large grains. This is the photoluminescence spectra of the samples. It's well known that the CCTS samples has a band gap around 1.4 and 1.5, between 1.4 and 1.5. So here you can see this peak is slightly different from the 1.4. So it's attributed in the literature to not to band-to-band transition, so it is attributed to conduction band to acceptor level transition. So due to the some defect or impurities in the band structure. Here also you can see in the B-type samples they are close to band gap values of the CCTS samples, except for this sample. So in this sample and also observed maybe some impurities and defects in the band structure. Our conclusion, it can be seen that CCTS thin films were successfully prepared by two-stage process using both stacking order, two stacking order and different reaction temperatures. Most of the films have a copper poor and zinc rich composition, but it was seen that this reaction temperature has a significant impact on the chemical composition. Excited patterns displaced the diffraction planes of the CCTS regardless of the stacking order and sulfurization temperature, and some additionally copper and tin-based secondary phases were observed in some films. Formation of Kestrel CCTS phase was confirmed by Raman spectroscopy, and also existence of CTS phase was distinguished for some CCTS films. Dense and polycrystalline surface microstructure were observed in SCM image. PL spectra of the films demonstrated the CCTS samples prepared using A-type have a purer band structure with respect to other samples. Overall, according to a performed analysis, CCTS samples fabricated using reaction temperature at 550 with the copper tin zinc as copper precursor stack revealed more promising results for potential solar cell application in terms of the structural and optical properties. Our special thanks to TÜBİTAK, because this research was supported by the Scientific and Technological Research Council of Turkey with this project number. Thanks for your attention. If you have any question, I can take it. Thank you again.
Thank you very much for the talk.
Thank you.
So, just to clarify for people not directly in the field of thin films, so the CCTS films are just being prepared by by different methods, I'm assuming, but the method that you guys applied, is how is that different than the methods in the literature, and is there any clear benefit of the method that you applied?
Are you asking a novelty of this study or for preparation methods?
Novelty of the method of preparation.
Yeah, of course. Yeah, in the literature, when you prepare the CCTS thin films, you can use the solution-based method or vacuum-based method. If you choose the vacuum-based method, you can use like a thermal evaporation or like a sputtering. But in the sputtering also, you can use co-sputtering technique or sequential layer deposition technique. But if you choose the sequential layer deposition technique, the stacking order of the films very important, because if you change the order of the films, you can obtain very different properties of CCTS thin films. So in this study, we compare the role of the zinc and zinc S layer in this study. At the first time, we propose this stacking order and to compare the reaction temperature and stacking order of the films.
I see. Okay, thank you. And do you have the infrastructure at the university for converting these films into solar cells? Is that one of the plans for future plans?
Yeah, we have a nice infrastructure for the thin film deposition, especially for the silicon. But now we have also started to fabricate thin film solar cells like a Ccts, CIGS, and also some of my colleagues start to study cadmium telluride thin films.
Okay, so these films that you prepared are just going to end up being in devices in the near future then?
Yeah, our next step is to make some solar cells, and also we prepare them, but I couldn't measure them due to this pandemic region.
Oh,
yeah, I am at home.
You're all affected by that, unfortunately.
Yeah.
Is there any other questions? If there's any questions that's written from the system, I don't see any that has been directed to me or anyone from the audience here in the chat. Seems like everything was clear. Okay, thank you very much.
Thanks, Dr. Görkem.
Move on to our next speaker. So for the session 16 film solar cells 2 today, our last speaker is going to be Bünyamin Ünsür from Yozgat Bozok University in Turkey. I'm hoping Dr. Ünsür is with us here to be able to answer questions at the end of the presentation. His talk is going to be on impact of RBF post-deposition treatment on cadmium sulfide and CIGS selenide and zinc oxygen sulfur CIGSE interfaces, a comparative HXPES study. Okay, so there's so CIGS. How do you pronounce it, John? CIG?
Yes, CIGS.
CIGSC?
CIGS simply, yes.
Okay. So so because in the title it says SC, so is it selenium instead of sulfur?
Yes, it's selenium.
Okay. And HAXPES method is
HAXPES.
Okay.
HAXPES, hard X-ray photoelectron spectroscopy.
Can you repeat it again? Sorry.
Hard X-ray photoelectron spectroscopy.
Okay, that's the first time I heard about this the method, so it will be interesting to hear about that. So with that, I'll just give the floor to you, and then we'll just come back for the questions. Okay.
Hello everybody, welcome to my presentation. My name is Bünyamin Ünsür. I am working at Physics Department of Yozgat Bozok University. The title of my presentation is Impact of Rubidium Fluoride Post-Deposition Treatment on Cadmium Sulfide CIGS and Zinc Oxysulfide CIGS Interfaces, a comparative HAXPES study. My presentation will start with a brief motivation. Then I will present the experimental method and the samples under investigation. Finally, I will discuss the results and finish with a brief summary. Let me first briefly explain how a CIGS-based thin film solar cell looks like. The CIGS absorber film is usually deposited onto molybdenum back contact using physical vapor deposition with a thickness of about 2 micrometers. The PN junction is formed between the P-type absorber and N-type buffer window system. The cadmium sulfide, or alternatively zinc oxysulfide buffer, is responsible for the formation of an electrically favorable junction in terms of band alignment at the interface. Therefore, the main motivation of this work is the investigation of CIGS buffer interface. In addition, it is well known that alkali metals play a crucial role in CIGS-based thin film solar cells. In 2013, a record efficiency of around 20% was obtained using potassium fluoride post-deposition treatment, whereas in 2016, even a higher efficiency of more than 22% was achieved using rubidium fluoride post-deposition treatment. Therefore, our second motivation is to investigate the impact of rubidium fluoride post-deposition treatment on CIGS cadmium sulfide interface. A recent record efficiency of more than 23% has been obtained by the application of cesium fluoride post-deposition treatment on CIGS absorber and using an alternative zinc-based buffer layer. Therefore, in this work, we aim to also compare CIGS cadmium sulfide and CIGS zinc sulfide interfaces. The experimental method we used in this work is X-ray photoelectron spectroscopy, HXPS. If we look at the universal curve of the inelastic mean-free path, kinetic energies between 10 and 1000 electron volts correspond to an inelastic mean-free path of about 2 nanometers. These energies can be achieved using standard lab-based X-ray sources like magnesium K-alpha and aluminum K-alpha. If we somehow increase the kinetic energy of the photoelectrons, we can correspondingly increase the inelastic mean-free path of up to 10 nanometers. So using high energy X-rays, we can investigate the absorber buffer interface if we could have a buffer layer with a thickness of below 10 nanometers. High energy X-rays can be obtained in synchrotrons. The HXPS measurements in this work were performed at BESI-2 electron storage ring located in Berlin. In BESI-2, there are several beamlines available for various purposes. We performed our measurements at the high end station, which is located at KMC1 beamline. The advantage of using this end station is that we can tune the X-ray energy between 2 and 12 kiloelectron volts. This provides us a non-destructive investigation of the corresponding interfaces. Now, I would like to briefly present the samples under investigation. First, CIGS absorber films are deposited onto molybdenum coated glass substrates using three-stage co-evaporation process. The bulk copper to indium plus gallium ratio was adjusted to 0.95. Rubidium fluoride post-deposition treatment was applied onto 2 samples, whereas the other 2 were kept untreated. Then cadmium sulfide and zinc sulfide buffer layers were deposited onto treated and non-treated absorbers using chemical bath deposition. The treated and non-treated samples were dipped into the same bath of either cadmium sulfide or zinc sulfide. In order to observe the role of the absorber composition, we prepared similar set of samples with copper to indium plus gallium ratio of 0.8. Now, I will briefly discuss the impact of rubidium fluoride post-deposition treatment on CIGS cadmium sulfide and CIGS zinc sulfide interfaces. In order to have a dependent information, we performed XPS measurements using X-rays with energies of 2000, 3000, 4000, 5000, and 6000 electron volts. The survey spectra of all the samples are plotted in the same graph here for an overview. The spectra are recorded with 3000 electron volt excitation energy. On all the graphs, we can see either cadmium or zinc and sulfur-related peaks originating from the top layer, cadmium 3D, zinc 2P, and sulfur 1S. At the same time, absorber-related peaks, namely copper 2P, indium 3D, gallium 2P, and selenium 2P core levels are also visible. Therefore, we can simply say that the information depth includes the inferred interface region. So we can say that the analysis of the interface region is possible. In order to get a quantitative information, we recorded the detailed core level spectra of all the constituent elements. We then integrated them over a Shirley background using Voigt profile, which is a convolution of a Gaussian and a Lorentzian profile. The signal intensity of an individual peak is then calculated as the area of the Voigt profile, the blue area here. The intensity of an individual peak is then related to many factors. Therefore, it has to be normalized to these factors before any comparison between two different peaks. The normalization factors are listed here. C is the concentration of the corresponding element. N is the number of scans. I0 is the incoming beam flux. Sigma, partial subshell photoionization cross-section. T is the transmission function of the photoelectron spectrometer. And finally, lambda is the inelastic mean free path of the photoelectrons. After applying necessary normalization procedure to recorded data, we calculated some elemental ratios for all samples and compared them. In this slide, I present copper to indium plus gallium ratio. The dashed lines in this graph represent the nominal bulk values. It is a known property of CIGS solar cells that the absorber presents a pronounced copper poor surface. This can be seen in copper poor sample in figure C. The relative copper concentration there lies well below the bulk value. Application of PDT induces a copper depleted region towards to surface, which can be seen as a downward curvature of the red colored data in both cases. However, this effect is more pronounced in case of copper poor sample in figure C, where the copper depletion goes up to the last data point, whereas the effect is limited to very surface region of copper-rich sample in figure A. If we compare the figure B and D, relative copper concentration of untreated copper-rich sample lies around or a little below the bulk value as expected. However, the ratio for the copper poor sample in figure D lies slightly above the bulk value. This can be explained by a partial outleach of a copper species in the beginning of the deposition process into the chemical bath. So they form probably a mixed compound together with zinc sulfide. The RBF PDT did not lead to any significant variation in copper concentration in case of copper poor sample. On the other hand, in case of copper rich sample, copper atoms seem to be driven from interface to absorber as a result of PDT. The following slide, I compare the gallium to indium plus gallium ratio of the samples. If we compare figure A and B, these are very similar. Both show a gallium enrichment on the surface before PDT, which is not influenced by the type of the top layer. Therefore, the high gallium concentration on the surface near region is probably related to the three-stage deposition of the absorber. After PDT, the relative gallium concentration with respect to indium strongly decreases in both cases. This effect can be explained by the formation of gallium fluoride secondary phases due to RBF PDT and removal of them by ammonium-containing chemical bath. Comparing figure C and D, a reversed effect of RBF PDT on the gallium concentration can be observed. This is again something directly related to the type of the absorber surface. In terms of the absorber buffer interface, there is almost no difference. Another important aspect is the diffusion of buffer layer elements into the absorber. One of the well-known phenomena in CIGS solar cells with cadmium sulfide buffer layer is that the high efficiencies are attributed to cadmium diffusion into copper vacancies of the surface near region during the chemical bath. Now here, if we compare figure A and C, one can see that the relative cadmium concentration with respect to copper is higher in case of copper poor sample in figure C already before PDT. This is a direct indication for a copper vacancy assisted cadmium diffusion into the topmost region of CIGS absorber. Cadmium diffusion is even enhanced by the application of RBF PDT. This can be seen as a slight upward shift in figure C. This is explained by the formation of a rubidium-containing layer on top of absorber and an ion exchange mechanism between rubidium and cadmium in that layer. Since the thickness of the rubidium-containing layer is proportional to the concentration of copper vacancies, the effect is most visible in copper-rich sample in figure A. When it comes to zinc diffusion, the effect of copper vacancy concentration and the RBF PDT appears to be negligible in comparison to cadmium diffusion. This is explained by the differences in their ionic radii. Zinc ion has a larger ionic radius than that of cadmium ion. As a result, the activation energy for zinc diffusion into CIGS is higher. It is therefore that an annealing step right after the chemical bath deposition of zinc sulfide is usually necessary to form a favorable junction. With this, I would like to summarize our findings. We found a strong relation between cadmium diffusion and copper vacancy. We found that rubidium fluoride post-deposition treatment leads to an increased cadmium diffusion in case of relatively copper-poor sample. The copper-rich sample is not affected by RBF PDT in terms of cadmium diffusion. We found that the variation in gallium to indium plus gallium ratio distribution can be dominantly attributed to the rubidium fluoride post-deposition treatment, but not the type of the buffer layer material. Finally, we found that zinc incorporation into copper vacancies to form donor-like zinc copper plus states does not occur as much as cadmium copper plus states. Thank you very much for your attention.
Okay, thank you, Björn Hocam. Is there any questions from the audience here? I haven't seen any questions from the chat. Okay, I'll just give you some time now while I ask my question. I was just wondering the conclusions that you had after the measurements at Bessie. By the way, I was able to visit Bessie. We were there for a meeting, and not for EU project meeting. It wasn't directly a research effort, but they were installing actually a new line to the system, so it was off. So we were able to actually go inside the entire thing and just, you know, we walked basically on that circle that you showed with Iver showing us the side and explaining. So it was quite cool actually. It's a really nice research facility they have down there.
Yes.
My question is the final understandings that you had from rubidium fluoride post-treatment that you mentioned in your conclusion slide. What are the implications of these findings on the possible performance of the solar cells that would be fabricated with the influence? Is there any repercussions for fabrications of performance?
You are asking about the performance of the solar cell.
Yeah, I mean the findings that you found for rubidium fluoride treatment, you know, how the zinc vacancies and copper vacancies are affected, and all of those. Does these have any relevant repercussions for solar cell performance?
Okay, I see. In general, copper vacancies are favorable for the performance of the solar cell, because in case where you deposit cadmium sulfide on top of the absorber layer, cadmium atoms are prone to diffuse into copper vacancy places, and there they form donor-like states, and it has a favorable effect on the performance of the solar cell. But in case of zinc sulfide buffer thin film, zinc atoms are bigger, and therefore the activation energy for the diffusion of zinc atoms into the copper vacancy places, it's hard. Therefore, in general, right after the deposition of thin film zinc sulfide buffer layers, it is needed to make an extra annealing step for the diffusion of zinc atoms. So if you apply rubidium fluoride post-deposition treatment, we saw in this study a direct effect in case of cadmium diffusion. There are a lot of different scenarios. They say that if you perform rubidium fluoride post-deposition treatment, you form a very thin extra top layer, including rubidium, indium selenide secondary phases. And then if you then deposit cadmium, your cadmium sulfide buffer layer, there rubidium atoms and cadmium atoms are exchanging. Then it is indirectly influencing the cadmium diffusion. But in my work, I did not see this direct effect in case of zinc sulfide deposit buffer. It is maybe because of the size of the zinc atoms or something different. I don't know yet. Really, yeah.
Very interesting. Okay. Thank you very much. If there's no other questions, I guess this is the end of session. This was 6, right? Session 6, Thin-Film Solar Cells 2, and there's going to be a lunch break now, and then the session 7 will start at 2 with Müge from Mtes on 2D perovskite solar cells. Well, she's actually my student, so she has some interesting results. So I encourage everyone to attend to that. It's going to start at 2, and the chair is going to be Dr. Antonio Agresti from University of Rome. And with that, thank you very much for everyone who's attended this session, and you know, keep having a nice meeting. And hopefully we will be able to see each other and interact with each other in the next Pvcon with this pandemic dissipated with the new treatments and vaccinations, hopefully. Okay, thank you all. Bye.